Welcome everyone to our seminar today. Our speaker is Jonathan Block, a longtime friend from Penn. So Jonathan is going to tell us about the singular foliations and the characteristic classes. So please.
Great. So let me just sort of tell you the kind of theorem that is the prototype. I mean, the people who study singular foliations in noncommutative geometry, I'm not sure they're as aware of this old theorem of Bauman-Bot that I've grown to really love. So let me just sort of, I'm going to do a review of some of the ideas in that. So the first thing is I just want to remind you about the good old-fashioned Poincare-Hopf theorem. Actually, this is stupid. Let me just bring up the whole thing. Okay, there we go. So M is a compact smooth manifold, C a vector field with isolated zeros. And the Poincare-Hopf theorem tells you that the Euler characteristic is equal to the sum over the zeros of the degree P of C, or sometimes it's called the index. And so the definition is that you take a point in the zero set and you define the degree of P of C to be the degree of the map that you form out of the vector field around the point that maps from the n-1 sphere of radius epsilon, just choose coordinates, it doesn't matter. And it goes to the sphere of radius 1 in the tangent bundle, and it's just given by the f of p equals c over the absolute value of c. Okay, so obviously I've made some choices, but it doesn't depend on any of the choices. It doesn't depend on the coordinate neighborhood, and it doesn't depend on whatever absolute value I'm using. Okay, but the reason I did this is I just want to point out that this formula, this definition of degree, is really local in the sense that it requires the entire germ of C about P. For example, you could have the vector field vanishing to infinite order at P. Nevertheless, this theorem is still true. On the other hand, if you have P as a non-degenerate zero, then you also have an infinitesimal formula. So I'm sort of stressing the difference between local and infinitesimal. Infinitesimal means you're basically calculating it on the jets, in this case, just on the tangent space. And okay, and there's also, I should point out that there are some beautiful generalizations of this by Eisenbud and Levine, that you don't have to require it to be non-degenerate, but you do have to require it to be, better, it can't vanish to infinite order at zero, but it's a very beautiful theorem. Okay, then I want to talk about these two theorems of Bot. The first is called his residue theorem, the Bot residue theorem, and it takes place on a compact complex manifold. And it says, given a holomorphic vector field C with an isolated zeros on a complex manifold, and you choose phi, a symmetric polynomial of degree n, okay, so that you can form characteristic classes corresponding to phi. And this theorem of Bot says that the characteristic class of the tangent bundle, the complex tangent bundle of M, which is isomorphic to the real tangent bundle, although it has a complex structure so that you could take Chern classes, is equal to the sum over the indices of the field C with respect to phi at the points P. Okay, so here there's a formula for the index sub P of phi in C, and it's given by this. So this is an infinitesimal formula. And well, there you go. There, I mean, it's right there. Okay, and the other theorem of Bot that I want to point out is, oh, before I get to that, I just want to say that this theorem was kind of generalized up the wazoo by Bot in particular and others, Baum and Cheeger and Baum and other people, to the case of non-isolated zeros, the case of meromorphic vector fields, the case of killing vector fields on a Riemannian manifold, and so forth. Okay. Okay, the other theorem I want to mention is probably better known, is the Bot Vanishing Theorem, which just says that you have a manifold with a distribution, then if it's integral, the Pontryagin classes of the normal bundle, T mod F, vanish above a certain degree. Okay? And in fact, it's a stronger statement than that. You actually get the forms representing the characteristic classes themselves actually vanish, that they're not just zero in cohomology, that the forms representing them are zero. And using this is what got the whole, well, maybe not the whole, but using this, you can define secondary characteristic classes and so forth. Okay, I'm actually going to only talk about primary characteristic classes today. Okay, and then Baum and Bot kind of did a pullback square of these two theorems. So it was in this paper here in 1972. And let me just sort of go here. So it was in this paper. So what their idea was, first of all, if you have a vector field C, it determines a foliation. Okay, and its singularity set is exactly the zeros of C. Okay, and so if you work on the complement of the singularity set, Bot vanishing implies that the form representing the Chern class of N is zero. Okay, and so with a little work, you futz around with things, you can basically show that the characteristic classes representing the normal bundle of the associated foliation is in fact concentrated in an arbitrarily small neighborhood of the fixed points, of the zeros. Okay, and in this case, right, I mean, here we have N. I should point out that N, has a nice resolution, which is just TM, and then you have the trivial bundle mapping into it by multiplication by the vector field. Of course, N and T of M have the same characteristic classes. Okay, so that's why you have the same characteristic classes. Why TM and N have the same characteristic classes. Okay. So what Baum and Bot did was they replaced vector fields by singular foliations, at least in the complex analytic sense. So a complex analytic, so their theorem is this: you take a complex analytic manifold, Tm its tangent sheaf, and F an integrable subsheaf of Tm. So of course, an integrable subsheaf, well, any subsheaf of Tm is coherent. If you don't know what that means, don't worry about it. And then you form the normal sheaf, n equals Tm mod F. Okay. And then you take the polynomial again, which is going to give rise to characteristic classes. And now you look at a component of the singular set of F. So the places where the foliation is singular. So if you like, you can describe that as exactly the points where the sheaf N is not locally free. It's not, yeah. Okay. And their theorem was that there exists a local formula for the characteristic class. It's actually a formula for the actual characteristic class of the normal bundle, at least if phi is in the vanishing range of the Bot vanishing theorem. So there exists a cohomology class, res phi of f comma z. So it depends on phi, and it depends on the connected component of the singularity set. And in this case, it's in the homology 2n minus 2l of z comma c. And it only depends on phi and the local behavior of the leaves of f. Okay, and if f is compact, then you have that if you sum up over the singularity sets of these residues, and then you take it into cohomology, that it actually equals the characteristic class of n. Okay, so here mu star is just the map that sends a homology class in Z to a cohomology class in M. Okay, it's just the composition of the inclusion on homology together with the Poincare duality isomorphism. Okay, so this is the theorem that I want to generalize. Okay, so my goals, I'll tell you the first two goals are, I think, accomplished, and the third goal is yet to come. So first of all, as I said, this theorem of Baum and Bot is local in the sense that it depends on, well, in the analytic situation, of course, local and infinitesimal are more or less the same. But I want to extend this to smooth manifolds, not just holomorphic manifolds. I'd like to make the proofs more conceptual, and I'd like to get infinitesimal formula for the residue. Okay, so something like the formula of Bot in the case of holomorphic vector fields. They actually proved they did get a formula, an infinitesimal formula, Baum and Bot in their paper, but it's actually it only applies in certain cases, and anyway. So yeah, I don't. And it certainly doesn't apply in the real situation in the case of smooth manifolds. Okay, so that's what I would like to accomplish. Okay. So the first thing I want to point out is that is it making people nauseous when I scroll through? All I'm doing is scrolling through so that there are all of the overlays appear at once rather than come out one at a time. Okay, so what I want to point out is that a DGA is a interesting and convenient and calculationally useful way to encode descent conditions. Okay, so what do I mean by a descent condition? A descent is basically the following: you have a map from X to Y, and you have an object, a vector bundle or a sheaf on X, and you want to know under what conditions does it descend to Y. Okay, so you all are familiar with this in some contexts, and I'll get to those in a second so that you understand what's going on. But that's the general issue of descent. Okay, so here what I want to point out is that if you basically have a differential graded algebra, and you define and you look at flat connections, I'm going to call a module over a DGA to be a finitely generated projective right module over A. So I'm going to use just plain A to be the A0, so it's like the functions. I want it to be generated, I want it to exist in non-negative degrees. Okay, so that, what do I want to say about that? And my D is, and I use cohomological grading. So D maps up in degree. Okay. So basically, all I'm saying is that a module over my DGA, I'm just assuming to be a finitely generated projective module over the functions together with a flat connection. Okay, and when you do this, you get some sort of well-known phenomena. Okay, so if you have M a manifold and U alpha a cover, and you let E alpha be a vector bundle for each U alpha, okay, and you have G alpha beta mapping E beta restricted to U alpha beta. U alpha beta is, of course, the intersection of U alpha with U beta. So you have an isomorphism on U beta with U alpha restricted to U alpha beta, and they satisfy a cocycle condition. You might also have to, you want to require something like whatever, G alpha alpha is 1. Then the E alpha is glued to give a global vector bundle on M. Okay, so the category of vector bundles on M is equivalent to the category of vector bundles on the disjoint union of U alphas with descent data. So here, if you want to put it in the context that I said before, you have the disjoint unity of U alphas, and it maps into M. And the question is, when does an object on this guy here descend to M? And this is a classic question that you're familiar with, and the answer is you have cocycles. Okay, so we're going to encode the descent data into a DGA. So if you let U denote the check groupoid correspond to the open cover, just as usual. I'm assuming people know what the check groupoid is. You get a corresponding simplicial manifold with UN is just the n+1 fold intersections of the open sets. Okay, so the UN the simplicial manifold in degree n is U sub n is by definition that thing there. This thing here. And then, by the way, Nigel was the one that told me how to use that guy. And you form a DGA, a natural DGA from this thing. And it's just kind of what you imagine it to be. It's, the things in degree n are just the smooth functions on UN. The differential is just induced by the simplicial maps. Multiplication is the usual simplicial product. Okay, the front face, back face product of things. Okay, so this forms a nice DGA. And now you get the following. So a module, as defined above, for the DGA C dot of U is the same as descent data. Okay, it's a module over this, so so I'm basically putting a flat connection on each U alpha. Sorry, not a flat connection. I'm putting a vector bundle on each U alpha, and I have a flat connection on the direct sum of this. And what you see is that a flat connection for this DGA is exactly the same as the cocycle relation that I talked about above. Okay, so you get that the category of vector bundles over M, so modules over C dot of U D. So again, let me just remind you that modules over the DGA right now mean for me flat, modules which are projective of the C0 and have a flat connection with respect to this DGA. And it's just exactly equal to the descent data on all of on the objects. And so you should also note that this works for any smooth group by G, and in fact for any simplicial manifold. Okay, for any simplicial manifold you can define this, and higher stacks are examples of simplicial manifolds, or I should say they're represented by simplicial manifolds. And right, so all of this applies very nicely to quite general relations. Okay, so all I'm pointing out here is that classical descent is an example of this. But now let's look at X, a complex analytic manifold. And if you take the Dobel GDA, then Grothendieck and Malgrange proved that if you look at modules over this DGA, you get exactly holomorphic vector bundles on X. Okay, this is a very classic theorem. But you can view this as descent that goes from the topological space X top, right? So the question is, if I have a vector bundle, E, a vector bundle over X top, meaning just a topological vector bundle, when does it descend to E to X analytic? When does it descend to an analytic vector bundle? Okay, and again, the point is that it should have a flat D-bar connection. Okay. And finally, foliations. If M is a smooth foliation, then there's a famous DGA that corresponds to it. So F right now is just a regular ordinary foliation, and you have F sitting inside T as an integrable distribution. And you form this algebra A dot, which is, my notation is that it's A dot of X comma F with D. It's the C infinity sections of the exterior algebra on the dual of F. So here D is defined by the usual Cartron formula for exterior differentiation. And modules over this DGA are called foliated bundles. Right? So this is Camber and Tunder, I mean, probably other people too, define this. And the idea is that this is what it takes to descend a bundle from the topological space X to the quotient space M mod F. Okay, where M mod F, well, you have to think about what you mean by that. Okay. Okay, so I mean, I haven't checked this, but my guess is that if you think about this, that a module over this DGA probably should give rise to a module not over the foliation C-star algebra, but over the algebra, what do you call it? Where you don't take holonomy, not the holonomy groupoid, but the monodromy groupoid, where you don't mod out by, it's a bigger groupoid. I haven't checked that, but that seems like the natural thing to check. Okay, so now I'm going to talk about homotopy descent. Okay, so now we're not going to glue things together according to isomorphisms, but we're going to glue them together according to homotopy isomorphisms, if you like, or homotopy equivalences, or whatever that. So this is contained in a paper of mine from long ago. But the input data is the same thing. You take a DGA, take a DGA, and we're going to find a DG category. Okay, if you don't know what a DG category is, it's not important. The only thing that's really important here is what an object of this category is. So an object, E, is in P sub A dot, which is called a cohesive module. So just beware that this version of cohesive has nothing to do with cohesive in the sense of people who do, what was it called? I guess I'm thinking of Urs Schreiber and his works. He works in a cohesive topos or something like that. It has nothing to do, at least as far as I know, with that. I chose the word cohesive because it is similar to coherent. Okay. So an object is just a z-graded but bounded in both directions right module E dot over A, which is finally generated and projective. And you have a z-graded connection, okay, that satisfies the integrability condition that the curvature, which is the square of E, is 0. So I guess I do feel, for people who aren't familiar with what this might mean, I should probably write down here. So E is going to have terms of various degrees. E will map, well, E will be equal to the directs, well, to a sum of EK, where EK maps E, the thing in degree dot, maybe I should give that a name, J, and it maps it to EJ tensor over A, those are the functions, with A K. Okay, and to be of degree 1, it has to map to EJ K minus K plus 1. Okay, so there are terms of each degree K where K runs over the degree of AK, and E squared equals 0 is exactly the condition that, well, it's a bunch of conditions, right? So it's equal to E0 composed with E0 is 0. So it's the 0th condition. So that just says that this complex of differential forms is this complex of, sorry, what am I saying? This complex of vector bundles or projective modules is a complex that with respect to E0. I should also probably say that EK is linear if K is not 1. Okay, for E1, it acts like an ordinary connection. Okay, the condition 1 is that E1 composed with E0 plus E0 composed with E1 is 0. So this just says that E0 as a connection, as a map, is covariantly constant with respect to E1. 2 is that E1, excuse me, E1 squared plus E0 E2 plus E2 E0 is 0. So in particular, E1 squared isn't 0. It's not a flat connection, but it's flat up to homotopy. Okay, and so forth. You have a condition for each n up to the dimension, up to the point where the DGA has no elements. Okay. So that's what this condition that Fe of E, that the curvature of E is zero means? It means all these conditions here. So it means that you have a complex of vector bundles or projective modules. It means that the the connection part of the super connection E1 is intertwines the differential. It means that it's flat up to homotopy and plus higher guys. Okay. And of course, and then you define morphisms of degree k between cohesive modules and so forth. Okay, I'm not going to dwell on that. Okay, so let's look at examples. So if we look back to this example where you looked at the open cover of a manifold, and this DGA that you formed from the groupoid or the simplicial space, then when you take this this DG category, you get exactly Toledo and Tong's twisted complexes. Okay, and if you take the Dobo complex, then you get something which is, in some ways, I feel very interesting, which is that, I mean, partly because it's due to me, is that P-A dot is an enhancement of the derived category of sheaves on X with coherent cohomologies. So the point here is that if you take, when you have a DG category, you can it just means that the morphisms between any two objects is a complex, and you can form the associated homotopy category. And the statement is that this, in this case, this is equivalent, I should use equivalent, to D co of X, maybe bounded with the setup that I've done. Okay.
Okay.
So,
can I make a comment?
Sure.
This theorem actually is true for also non-compact complex manifolds. So I think it's proved by Lazarev and Holstein and Chuang in 2018. So yeah.
Okay, I don't know that, I'm not sure I believe that, but I'll look. I mean, the point is that when you're a non-compact manifold, you have lots of objects that are kind of weird. Namely, there's no, I mean, I feel like, but from my definition, that this guy here has some finiteness at infinity built in, whereas DB-co, you can have all sorts of weird things like, you can have...
They replace the right-hand side by the so-called globally bounded complexes of coherent sheaves.
Oh, okay. Okay, I believe it. Yeah, that's fine. I believe that that's true. I mean, the only reason I do with compact is that it, that it's, it hypothesizes away the issues having to do with what's happening in infinity. I mean, what do I want to say here? I mean, the issue with what happens with non-compact manifolds is actually just an issue about sheaves on smooth manifolds. It's really, right. Okay, let me just continue. Oh, okay. That's actually all that I have prepared in slides. Okay. So now I have to go to my Luddite self. Okay. So I should probably say that this is joint work with King Yun Zheng. I don't really know how you pronounce his first name. I call him Andy. So, okay. So, so what I want to talk about now is get finally back to foliations. So first of all, let me remind you or talk about just regular foliations to start. So FTM smooth distribution on M, and which is integrable. And let A dot MF be the DGA that I defined before. So this as the elements of this DGA are the smooth sections of the exterior power of the dual of F, and then D is defined by the by the exterior algebra. Okay, and let me remind you that nu, well, it's by definition Tm mod f, the normal bundle to the foliation. Yep. Okay. What we know is that, in fact, Bot constructed a connection, a partial connection. In fact, it was motivated by the situation with complex manifolds, but you have a connection that maps smooth sections of M with coefficients in nu. So this means C infinity of M comma nu. I've come to write A instead of C infinity because it takes fewer strokes. And it goes to A M nu tensor A, that's just the functions on M, with a 1 of M comma F. And it's just given by the standard form that B of a section, paired with a C. So here C is in F, is a section of F. Okay, so a one form, A1 of M on comma F are things that pair with elements, sections of F. And by definition, this is, you take pi C twiddle S, where here C twiddle is a lift of C to Tm. So you lift it to a full vector field. You take the bracket, and then you project back down to nu. No, I don't have to write. Pi maps Tm to nu. Yeah. So that's the Bot connection, and it's a partial connection in the sense that it really you can only evaluate it for elements of A1 of M comma F, and it is flat. Okay, so in particular, nu with B is an element of P A M comma F. Another way to think of that is that, of course, the normal bundle should be something that descends to the quotient. Okay. Okay, so now we have a diagram. Now we have the following diagram. We have a map. We have there is a natural map that goes from forms on M to forms on to this DGA. Okay, this is just dual to the natural map that to the natural inclusion. Okay, so let's call this. I'll call the natural inclusion rho because of Lie algebroids. So I'll call this rho hat for the dual. And you have the kernel of this map. So that's a bunch of differential forms. Contains no forms in degree 0 because, yeah, contains no forms in degree 0. Okay, and one thing that's kind of easy to see is that if you take A dot and you raise it to the kth power, that this is actually just 0 for k bigger than q. Whoops. For k bigger than q, where q is the codimension of the foliation. Okay. So, right. So now the point here is this. You have the following situation. You have, you have the normal bundle. It has this Bot connection, B mapping nu to nu tensor over A with A1 of M comma F. Okay. And then up here, we're going to have nu tensor over A with just the ordinary de Rham algebra of M. And there's this natural map here. And we're going to lift B twiddle. You can always lift. Bot showed you can always lift. It's not very hard to show that you can always lift, but you can. And what's true is that if you take the square of B, that this lies in the endomorphisms of nu tensored over A with I dot. Okay, so that means that if you take phi in C or R, I don't really care, of x1 through xn, and you pair it, and you take phi paired with B hat twiddle, this will end up being, oops, not bracket, pairing it. This will actually be in A dot, and therefore, if the degree of phi is bigger than k, you get vanishing. Okay. So what happens is you get vanishing of the characteristic classes in dimensions bigger than 2k. Okay. I mean, the point is that B twiddle squared has degree 2, so when you raise it to the kth power, it's in degree 2k, and so forth. Okay. So now, are there any questions? In fact, Zhang, I just want to make sure that people are still there. Can you hear me?
I can hear you.
Yes.
I think there's a question in the chat.
Oh, really?
Yeah, I asked a question. If you go back a page, I think you had the tilde on the wrong spot because Xi is a section of F, right? So that's F is sitting inside TM, so you don't have to lift it, but the S is in the quotient, which is in the normal bundle, so you have to lift that up. So the tilde should really...
Yes, you're right. Thank you very much.
Right. Okay, yeah.
Thank you. Yeah, you lift S. Yeah, you have to lift the section. Thank you. Okay, so now we're going to go on to singular foliations. Okay, and of course, what you mean by singular foliation is, well, I don't know. I guess it's not so ambiguous at this point. So in the complex world, in the complex analytic world, it's very simple. It's just a coherent subsheaf of the tangent sheaf, which is integrable. The analytic data kind of guarantee that there's enough tameness that that it's reasonable. But I guess ever since Sussman and Stefan, you've come across the following. You have F. So I'm using calligraphic F, a subsheaf of TM. So I'm going to write underscore for this. So with the underscore, it just means the C infinity sections of TM. Okay, so F is a subsheaf of TM. And you require not too much. And I'm going to let M be compact again for simplicity. I'm just going to require the F twiddle as an AM module. So AM is again just the functions on M is finitely generated. So this Stefan and Sussman, this is enough to actually have well-defined leaves to basically be able to integrate F. Is there a question? No. Okay, I'm going to have to actually require a little more. Namely, I'm going to ask that F is perfect. Okay, and eventually I'll have to ask a little more than that. Okay, so perfection, will guarantee that there are characteristic classes of F. And that, that because that's what I'm interested in. Maybe I should define what perfect means. Perfect means that it's better than anything else. That was a joke. Okay, so perfect means that there exists vector bundles, smooth vector bundles. T0, T minus 1, down to T minus L, that resolve F. So let me write this. Let me write the underscore for the smooth sections. Okay. So it just means that you have a resolution by smooth vector bundles, by sections of smooth vector bundles.
So
Okay.
aren't 1 and 2 basically the same as saying that it's coherent? I mean, as far as the complex situation is concerned.
Yes, if this were complex, then perfect would be equivalent to coherent. But in the there isn't really a very good notion of coherent in the non-complex world. And this is a replacement for that. Okay, so Grothendieck, and Illuzi in SGA 6, I think, basically they try to extend Riemann-Roch technology to the most general setting. And in particular, they don't want to require Noetherianness anywhere. So what they realized was that while the notion of coherent doesn't really make sense in the non-Noetherian case, there's a perfectly good notion for sort of a finiteness, at least if in the derived category, in the category of complexes. Okay, so just be wary that the notion, there is a notion of coherent over any ring, I think, due to Serre. And the problem with that is that if you look at C-infinity modules over C-infinity functions, that the coherent modules are very, very restrictive. None of the modules that you really care about are actually coherent in Serre's sense. Okay. Right. Okay. So that's what I'm going to require. F being perfect means that it has a resolution. And this was a situation that this Laurent Jeanjou, again, I apologize if I'm pronouncing their names wrong, Laveau and Strobel construct a generalization of A dot of M comma F. Okay, so, and basically it's just this. You take the dual of, so we have this complex T dot. That's called the boundary maps del. So these are just or maybe I'll call them del 0. These are just the alinear maps that resolve F as just an ordinary module over the functions. And we take the dual. This is the dual of this. So T dot was located in non-positive degrees and L dual is located in non-negative degrees. And A dot M F is by definition the sections, the C-infinity sections of M with values in the graded symmetric complex of L. We have to shift by -1 and so forth, okay? So there's a differential there, just the dual of the del 0. This differential contributes to the total differential here. So there's a differential here, D, which looks like D0 plus D1 plus etc., where D0 is just the extension of this D0. Oop. Let me hit erase instead of. Okay, is just the extension of this D0 to the symmetric powers. And D1 is actually something that actually differentiates, and D2. So you basically construct sort of degree by degree, you construct a differential that satisfies, reasonable things. Okay. And in the case when f is just a single distribution, a regular foliation, this is just what I mentioned above. Okay, they call this what do they call this? The universal infinity Lie algebroid. Okay, so there's an equivalence between Lie algebroids and differential graded algebras. Differential graded algebras are much easier to deal with than the usual definition of infinity Lie algebroid. But this is it. Okay. Now the thing that's nice is that if f is perfect, then n, the normal sheaf, which is by definition is just the quotient, is also perfect, right? Because n will have the resolution Tm, T0, T minus 1, all the way down to T minus L. Okay, so you can write this as T shifted by 1 plus Tm. And this maps to n. Okay, and so n is perfect. Okay, and you can still define a Bot connection. So there's a B which maps this complex, T shifted by 1 plus Tm, to itself. Maybe I should give this a name. Let's call this n dot. Oop. Why am I not erasing? Okay, there we go. So I'm calling n dot this. Oh, shit. This is T dot shifted by 1 plus Tm, and that's what I'm calling n dot. So there actually exists a Bot connection mapping n dot to n dot tensor over A with a dot of m comma f. Okay, it really requires that you have all these higher structures on it, as well as the higher elements of the differential. Okay, but the upshot is that you actually have a globally defined connection. It's not just, in the original proof of Bot and Baum, their Bot connection was sort of only defined off of the singular set. Here you actually get something defined on the entire, defined globally, and the homological algebra covers the subtleties. Okay. But, well, we still have the map that goes from a dot of m to a dot of m comma f. But this map doesn't have very good properties. This map, for example, well, in terms of homotopical algebra, this map is not a fibration, is the technical issue. Okay. Although I'm not actually using, so Newton showed, Juice Newton showed that there exists a semi-model structure on infinity Lie algebroids. Okay, I'm not really using his stuff. I'm just using, I'm not really using his model structure, but I guess one could. But in particular, the reason it's not actually model structure is there aren't fibrant replacements. Okay, on the other hand, we can construct an appropriate fibrant replacement just by hand, so that there exists, so maybe I should write that, not vibration. mean, in particular, it's not onto, but that's basically the issue. But you can construct an equivalence, let's call that iota, to A dot of M C of Tm. Okay, so C of Tm is actually another infinity Lie algebroid, if you want, and it maps here. So this is a quasi-isomorphism, and this map here is a projection that's actually onto, and it makes this diagram commute. Okay. So this is an infinity Lie algebroid equivalent to Tm. Okay. So here we still have an exact sequence, A dot to A dot of M C Tm, and then that goes to A M F, and it goes to 0. Okay, so now you can take, so by the way, so I just showed up here that, oops. So up here, where is it? Up here, this just shows that, gosh darn it. This shows that okay, maybe I'll do it this way. We just showed, or just, we didn't show it, but we stated it, that N with the bot connection is an element of P of AMF. Okay. On the other hand, we don't need to deal with this particular object of P of A dot M. We can deal with any object of P of A dot MF. Okay, and again, phi, a homogeneous polynomial. Okay, we know that E dot, oh, so you have the following picture. You have E maps by the connection to E tensor over A with A dot of MF. Okay, we also have this guy here, E tensor over A with A M CTM. Okay, this is the guy that's equivalent to just the ordinary forms on M, and there's a map going down. And I just want to pick a lift of this. So E twiddle is a lift of this connection, of the bot connection. And the same thing happens. E twiddle squared, it ends up being in the endomorphisms of E tensor over A with the ideal that I just mentioned up above. And therefore, phi paired with this E twiddle squared is really in I dot. But now you have the following. Well, we have that A of M CTM is in fact equivalent to A dot of M. But what is also true is that if you take A of M minus the singular set, this is the singularity set. Oh, I should say something about this. This lift, at least I can't show this lift exists in full generality. For this lift to exist, I need the foliation F to be locally analytic. Okay, meaning, so this condition just implies some amount of tameness for the foliation. So for example, it will imply that the singularity set is, I should say, locally real analytic. So it just means that that you can choose, that around every point, you can choose coordinates, smooth coordinates, so that the foliation is generated by real analytic functions. But this will guarantee that the singularity set isn't too messed up. In general, you can have a perfect foliation where the singularity set is a Cantor set or something like that. This hypothesizes that away. This is a condition that was told to me by Nigel, but I looked it up and it's actually in the paper by Laurent Jeanjou, Laveau, and Strobel.
Jonathan, somehow I cannot hear your voice.
Glad you said that, Guoliang.
Yeah.
Can you hear any of us, Jonathan? Because we can't hear you. And the Chief Shang has left, so.
Let's see.
I think it's just the internet connection, probably.
Do you think it would help if I make Jonathan the host instead of the co-host?
I doubt it. I think his internet maybe is disconnected. So.
Okay. But I see Jonathan on the list here. Okay, so Nigel is calling Jonathan, I think.
So I'm talking to Jonathan now, and we're trying to figure out what's going on.
Okay, good. Yeah, thank you. Sorry. I think, yeah, okay. Yeah, Jonathan just got back.
So you let me in?
Oh, yeah.
Okay, so where did I?
Like 3-4 minutes ago.
Okay. Okay, now it says only the host can share this meeting.
Oh, I can make you the host.
Or a co-host, right?
Let me see. Oh, yeah, I can make you the co-host also. Okay, yeah, now you are the co-host.
Okay. Okie doke. Oops, that's not what I wanted. Okay. Okay, so I'll back up a little bit. I don't know exactly where I went off the rails, but right. So we just showed that you have that this normal object is in this cohesive category, And hello? Okay. And right, so now, I'm just pointing out that you have, that what I'm going to say is true for any object in there. And so you would choose an object in P of A dot M comma F. So it's a homotopy flat object. You choose a homogeneous polynomial. And you lift the connection, the homotopy flat connection E from E dot, well, from going into the foliation DGA to going into the replacement of the de Rham DGA. Okay, so you lift it up to there. Of course, it's not going to be flat, and that's why you have characteristic classes. But it does have some properties with respect to the complex. And as I said, in order to do that lifting, I need an extra hypothesis. In addition to perfection, I need to require at least F is locally real analytic. Okay. So, right. So you take the curvature, and it ends up being in the endomorphisms of E tensor the ideal. And therefore, when you pair, you end up in the ideal. And now the point here is, and I should point out that when you take the lifting, maybe I should write it this way. The point is that you only need to that when you take the lifting and then you project back down to E tensor A dot of M comma F, I should write this down. When you lift, I need to stop soon. E from E to E tensor AMF to E tensor AMCTM. You only need to change, when you take the projection, so you take Q, you don't change anything outside an arbitrarily small neighborhood of the singular set. Okay. So the point here is that what you get is when you take this characteristic class, phi paired with E, total squared, and then look at it in A dot of M, this will be supported in an arbitrarily small set, arbitrarily small neighborhood, arbitrarily small complement. Sorry, this will be supported in a complement of an arbitrarily small neighborhood of sigma. Okay, and this is essentially the definition of the residue, and the residue theorem is a simple consequence of it. I should point out that one last remark, which is that by extending things from the bot connection to arbitrary objects in E tensor PAMF, there are a lot more objects in here in this sort of homotopy category than there are if you just look at, say, foliated vector fields, vector bundles, foliated vector bundles. In particular, if you take, a normal, if you take N, a closed submanifold of M transversal to the foliation, then in fact, there exists a class, or not a class, but an object, which you might want to, I don't know what you want to call it. I guess you can call it O-N, I don't know, in P of A dot M comma F. Okay, so this is a little bit like this is a little bit like the projection that Kahn constructs when you have a normal to a foliation. Okay, but right, so you have a lot more of those than you have global vector fields, which are flat, flat with respect to the foliation, than you do. Anyway, so the point is you have all these objects here which have geometric meaning, and so I think that's another interesting thing about this. Okay, so I'll stop here and have a drink. Any questions? Are people still there? Uh-oh.
Oops. Oh.
Did I, no, I'm still here, right?
Yeah.
Okay. Okay, so yeah, I'm done.
Okay. Any question or comment?
For your last result, do you have, so you mentioned that the pairing between phi and E square only depend on a small neighborhood of the singularity. So do we have, are you working on a formula for that pairing? So,
that's what I would like. So as I said, when in terms of my goals, so in terms of my goals, there, I have sort of, the local statement of the Baum-Bot residue theorem, namely, you can define this homology class, and it has the right pairing properties. But if you'd like an infinitesimal formula and for it, and that I don't have yet. And although I think, I mean, it's possible that this higher homotopy stuff might help come up with a sort of a cleaner formula, a clean formula. So that's one hope.
So high homotopy, Jonathan, high homotopy in which sense?
Well, I mean, this infinity, I mean, this DGA that we're talking about is an infinity Lie algebroid. So it's, it's not a Lie algebroid in the sense that the bracket satisfies Jacobi, but it satisfies Jacobi up to homotopy, and then it satisfies Jacobi up to, it satisfies higher versions of that as well. So that's, I mean, everything is up to homotopy. And also my objects. I mean, in order to get coherent sheaves, I mean, it's not true that on a complex manifold, a coherent sheaf has a resolution by vector bundles, but it does have a resolution in my sense. There's sort of a homotopy resolution. There's a resolution, maybe I should say it this way. There's a resolution by smooth vector bundles, which is homotopy flat. Okay, and that's good enough to work with the coherent sheaves. So I mean, you can work with coherent sheaves in this smooth setting. So for example, Baum and Bot use real analytic techniques to prove their theorem, and here you can actually, on complex manifold. Here you can just you can use just the fact that when you want to, so one of the things you can do is prove their theorem in a complex case, and you substitute my description of resolutions of coherent sheaves by, sorry, you replace their use of real analytic resolutions by my sort of homotopy resolutions, and it works much cleaner.
Any other question or comment?
Can I maybe ask you, maybe I missed it in the beginning, do you see any relation to recent work by Bertrand Toen and Vetsozi?
Yeah, so I looked at that. I mean, I talked to Bertrand about this. I mean, I talked to him several years ago about foliations, but his stuff is purely algebraic. So I don't see any way that their stuff can be extended in any simple way to this. you know, but somehow, well, the real answer is I don't know, but I'm guessing not.
I see, I see.
I think it's kind of a different direction.
Any other question, comment? Well, if not, let's thank Jonathan for a very nice talk.
Oh, nice.